So in addition to conditional probability, we also have a different type of way of considering events, which is independent, meaning that two events are just simply not connected, and there's different ways to show that and different ways to use that in terms of calculations, and let's go ahead and find out how to do that. So independent events are just two events that are independent. They're not connected in any way, like the probability of me wearing this shirt and the probability of my flight being on time, all right? At least I would hope so, in which case I would like to know because I want my flight to be on time. So if two events are independent indeed, we would say the intersection between those events is actually just the probability of one times the probability of another. That's how you find them both happening at the same time. So if you're actually asked to show if events are independent, we could use the above property, or we can say that, hey, you know what, the probability of A happening is the same thing as saying, hey, given that B happens, what's the probability of A? And that might look a little bit weird, but think about what that means. It means that the probability of A is the same thing as the probability of A given that B happens. But if they are completely independent of one another, it doesn't matter if B happens. It should be the same probability of A. So it doesn't matter if it's the probability of one thing given another thing. It should still be the same exact probability because it does not matter. It is not affected by the probability of the other event. Now, what that might look like in a problem. Let's say that we have a Venn diagram here that is going to show us the number of students in a class who study Spanish and the number of kids who study math. So I have Spanish down here, kind of poorly noted, and math up here. So let's figure out how we can show that these two are indeed independent events. And we are given our conditional probability here as well as our independent events here. And again, remember that it's the same thing here and here. Okay, maybe put that down in your notes. So let's say that we want to prove this in the A, where we're saying, hey, we're going to calculate this if they're independent or not, considering the values of P of S and then PS given M. So what that means is, hey, what's the probability of a kid studying Spanish? Well, the probability of a kid studying Spanish is going to be equal to what? Well, I'm going to have the probability of Spanish, which is going to be 8 different kids. And how many total kids do I have? I have 6 and 2, that's 8, plus 3 is 11, I have 20. So my answer is 8 over 20. I have 8 kids who study Spanish in total out of a grand total of 20 kids. Now, what's the probability of S given M? Well, that's the probability of the intersection of A and B given the probability of B. So let's think about the probability of S given M. So the probability of S given M is going to be 2 kids that do both the intersection between the two all over the probability of the second event, which in this case is math, which is going to be 2 plus 3. That's going to be 2 over 5. If I simplify this down, this would be 4 over 10, and this would be 2 over 5. So the probability of S does indeed equal the probability of S given M, because they're both 2/5. So they are indeed independent because the probability of one happening is not affected by the other. So now how can I show that? By considering the property that the probability of S times the probability of M, and then also the probability of the intersection. So the probability of the intersection here, probability of S intersect M, is going to be 2 all over 20. So what is the probability of S? Well, I actually already figured that out. That's 2/5. The probability of S is going to be 2/5. And then what's the probability of M, which is math? The probability of math is going to be equal to what? I am going to have 5 kids total out of 20. So I can now have 5 over 20. So now if I multiply these two, I take the probability of S times the probability of M. Well, 2 out of 5 times 5 out of 20. That would cancel, giving me 2 over 20. So I can see that the probability of the intersection between these two is equal to the probability of one times the probability of another, which again is one of my definition cases for them being independent. So those are 2 different ways that you can show that these events are indeed independent just by using these basic formulas. Now let's take a look at another example problem to see how we can use this even further. So in a consumer survey, 2,371 adults are asked questions. An adult is chosen at random from those taking part. So C is the event that the adult likes coffee, and then D is the event that the adult is called David. So now let's say that for part A, I'm given that C and D are independent events. Explain why this is the case. Well, just logically speaking, the probability of one liking coffee and the probability of one being named David, your name has nothing to do with your preference to liking coffee, just logically speaking. So you can kind of just think about, hey, the definition of an independent event is basically that these two probabilities have really nothing to do with each other. One does not affect the other. And that's exactly what this is. Liking coffee and having a name of David, they don't have any influence on each other, so they are independent events. But now, let's say that I'm actually given some probability numbers here. So let's say the probability of C is 0.8 and the probability of D is 0.007. Now let's interpret your answers in context in each of the following. So let's find the intersection of these two. Okay, so remember that if these are independent events, then that means the intersection, that the probability of C intersect D is equal to the probability of C times the probability of D. We were given that formula or definition from above. So the probability of the intersection is going to be 0.8 times 0.007. So the probability of C intersect D, meaning you like coffee and your name is David, is going to give you 0.0056 or about 0.56%. So that's not a very likely case, right? 0.56%, that's not very likely to happen. So how can I figure out what the probability of C union D, that you either like coffee or your name is David? So if you recall from above, we were given a definition that the probability of two independent events, like the union of two independent events, is the probability of one plus the probability of another, and you got to subtract the intersection. Now that might seem a little bit weird, but if you think about this, you're basically taking the probability of C. In fact, if I actually just drew a very quick Venn diagram here, so let's say I have coffee and then I have David. So if you think about this, if I want the probability of coffee, I'm taking out this entire circle. And then if I want the probability of, let me just say this in like that, the probability of coffee would be right here. And then I want the probability of being named David. You can kind of see right here that I am actually shading in this circle twice, meaning I have to subtract this intersection because I am counting it twice. It's shaded in twice here. So I'm just going to subtract one of them so that way it's only accounted for once and not twice. So what was the probability of C? Well, the probability of C was equal to 0.8. The probability of D was 0.007. And the probability of the intersection was 0.0056, meaning that the probability of the union of liking coffee or being named David is going to be 0.8104, meaning about an 81% chance that your name is David or you like coffee. Or your name is David and you like coffee, right? In either way, I have expressed this correctly. So what if I want to determine whether C and D are mutually exclusive, meaning that they cannot happen at the same time? Well, the answer just becomes a bit definitional, but if you remember that the probability of C intersecting D, if it's mutually exclusive, that means that there is no middle. The probability has to be 0 because there's no shared there's nothing inside both of the Venn diagrams. There's nothing in the intersection. However, I have a value for the intersection here, meaning that it does not equal 0. Therefore, these are not mutually exclusive events. Because if you think about it logically, again, you could be, yes, my name is David and I like coffee. Sure, both of them can absolutely occur at the same time. Being mutually exclusive means they can't occur at the same time. So what that means is that the intersection must be 0 for mutually exclusive events, which this is not. So since these are not mutually exclusive events, we know that the intersection does not equal 0, as we already proved in part B. So I hope that helped a little bit with how we can use the definitional properties, as well as just a little bit of math, as well as some Venn diagram representations on how to go about independent events. Hope that helped, and I'll see you all in the next video.